This next chapter is on equilibrium, and we were introduced to this concept last year. So let me grab an image here. All right, so for an equilibrium type of problem, we have to, first off, when we draw our free body diagram, we have to draw the forces at the point of contact. So you can see here that from looking at the diagram here, we can identify these forces acting at these different locations. The, I think, tough one here is this Rx and determining the direction at which that is pointing. So we have to reason out how the other forces are acting in order to determine what the force is at that pin. So if we look at another image, which is from last year's textbook, okay, these are showing the different types of connections. So for a frictionless surface or something that's on a wheel, there is only the upward force from the surface in contact with the support or connection, whatever the object is, the beam, the ladder. Okay, and the normal force has to act straight up because of the definition of what a normal force is. Down below, if it's a rope or just another rigid link, the force is going to be acting along that link or rope, just like a tension. If there is a rough surface, you can see here, again, the normal force has to be normal to the surface, and then we have to reason out what direction would that slide if there was no friction. So if it's not sliding, you have to reason out that the friction is going to be opposite the direction of its tendency to slide. And you can see that there is now an X and a Y component that would have a net along the length of that beam or whatever that is. And then there's a frictionless pin. Anytime there's a pin, you're just going to have an X and Y component that are representing the total force on that pin, whether it's a pin on the floor or pin on a wall. So first challenge is identifying all the forces in their correct directions. In order to continue, we need to define what equilibrium is. So equilibrium, and it's specifically in this chapter, it's static equilibrium, which means there is no motion whatsoever, so not even at a constant speed. So when an object is in static equilibrium, the sum of all the forces equals 0. And that's in the X and Y direction. But also the sum around the torques, sum of all the torques equals 0. Now when we sum up all the torques, we have to do that around a point, a reference point, so that we can look at the force at some radial distance away from a possible rotational point. Now, the sum of all torques equals 0 around any point in space. So if we looked at the problem above, the point does not have to fall on the actual beam. Now for this problem, at the pin is going to be the location you're going to want to do that. However, we can make that point any point in space. We can look at the point there. We can look at the point there. We can look at the point there. And all these forces will sum up to be zero. Sum of all the torques would always add up to be 0 if the object is in equilibrium, no matter what point you pick. It can be some random point over here. Let's look at a problem now. So here there's a beam that's attached to the wall by a pin. There's a cable that's also attached to the wall, and that cable goes horizontally to the edge of the beam, and there's also a mass that is pulling down at the edge of that beam. Now this beam also has mass, so there is a force of gravity acting at the center of mass of that beam. It gives us the dimensions from the pin to the cable, and from the cable to the edge of the beam. There is an angle there, but that is not given. What we're trying to find here is the tension in the cable. Here. All right, so let's draw all our forces on this free body diagram. We have a tension going down. We have a tension going this way from the cable. We have mg going down. We have a force of the pin holding that part of the beam upwards. And let's think about what direction in the horizontal is that pin exerting a force. Just by looking at your other forces, since the cable has a tension acting to the left, that beam is not moving to the left in the direction of that tension. So that means there has to be a force to the right. And now we have to pick our pivot point. All right, so we know the tension in the string with the large mass, because it's in equilibrium, the force of gravity pulling down on that block is going to be equal to the tension up on that block, which means that tension down has to be equal to the big mg. All right, so we know that. We're going to have to use that. We want to find Tc, so we can't use that edge point. We don't know how much force is upward at the pin, and we're not 100% on what Fx is either. So usually when there's a pin, this is the point that we want to use to reference all of our torques. So the next step is, let's sum up all of our torques with respect to that pivot point. So I'm going to make my downward forces a positive torque that would cause it to rotate clockwise, and the other direction would be counterclockwise and negative. There is a standard. I'm pretty sure counterclockwise is negative, but it doesn't matter because you can just move them from one side of the equation to the other and switch the signs. All right, so I have the tension pulling down at the edge of that beam. That is going to be equal to big mg, and that is acting at a certain distance away from that pin. Now, since torques are only the perpendicular distance, we're given that perpendicular distance, 2.5. So it's acting 2.5 meters away in that horizontal direction to that force. So we're going to use 2.5 as our radius there. We also have little mg, and that is acting a perpendicular distance of half of 2.5. And I messed up. This would be plus because it's acting in the same direction as the other torque. And then we have Tc. And Tc is also acting at 2.5. And all of that has to equal 0. So if we look at this, the only thing we don't know in that equation is Tc. So the sum of all torques is all we need in order to get this final answer. So we move everything from one side to the other. That we want to find here. And then divide everything by the 2.5. And if we solve that out, we should get that the force should be 6,093 newtons. If we continue, we can actually solve for the upward force on that pin as well as the horizontal force on that pin. And actually the horizontal force on that pin is actually pretty easy here. So if we summed up the forces in the x direction, set them equal to 0, we only have two forces that are going left to right. We have the f of x, and we have the tc. So that means f of x has to equal tc, which is the same 6,093 newtons. The other thing we don't know is the y component. Sum up all the forces in the y. Now my diagram is too small to see, but we have the Fy going up, big mg going down, little mg going down. Very simple math there. If we plug in our numbers, we'll get 5,047 newtons. So we can find every force acting at every point on these objects if we do all three steps. It's not always necessary. Usually if you get something right away from summing up all the torques that you can't get from summing up all the linear forces. And that is static equilibrium. So now we have to practice.